Hi everyone. I am back for external inductance. So last time, a while ago actually, I discussed internal inductance. I showed you kung paano siya kinukuha by using the formula for magnetic field intensity and magnetic flux density. Now, and that is just the internal inductance. Now, tingnan naman natin what is happening outside the conductor. How does your inductance behave when it's outside the, well, it's not really outside the conductor, but yeah, how does your current affect the magnetic field outside the conductor, and how does it affect yung ating inductance? Okay? So, before going to this discussion, I want you to take note of these two formulas from internal inductance kasi it's the same formula na gagamitin pa rin natin. We'll still be using Ampere's law, I over 2 pi x, and we'll still be using this formula of magnetic field density, which is mu h. Okay? So if we talk about the external inductance, your area under consideration is the one enclosed by X. Okay? So if we have this conductor, now let's talk about the area outside. Okay? So let's define an arbitrary point X again, same way na ginawa natin sa um, tawag dito, the same way na ginawa natin sa internal inductance. But in this time yung X natin is outside. That point X is outside this conductor. So now it's located here. Okay, so you still have this path of integration here. This is the path of integration of your conductor. Okay, then let's define, yeah. So from your mu h, then makukuha pa rin natin si magnetic flux density as mu I over 2 pi x. The same derivation sa ginawa natin on internal inductance. If you get the differential flux for a small space with this thickness, small thickness, differential thickness, and a meter length. Again, this is just 1 meter, the same dun sa ating internal inductance. So everything that will be solving here is in per meter. Okay, naka per meter unit siya. Okay, so your differential magnetic flux linkage, which is equal to your differential flux, is just B times differential thickness times 1. Okay? So yun. This is thickness times 1. Okay, so as you can see, para tayong kumukuha ng area. Okay? And that is mu I over 2 pi x times dx. Okay? Now, if you integrate between these 2 points, between D2 to D1, take note, again, the reason why it's between D2 to D1 is you want to get area outside the conductor. Okay? So, kinukuha natin itong area na to, outside the conductor. So, the flux linkage between D2 to D1, which is outside the conductor, is mu over 2 pi, which is this constants, mu I over 2 pi. And then, that x is integrated from D1 to D2. So, D1 to D2. Take note that x is in the denominator, so you have an integral of what's that, a fraction, 1 over x, so it's ln of d2 over d1. So yeah, that's basically it. Yan na yan, that's the formula for external. So mas madali lang siya as compared sa ating internal. However, the thing with internal inductance is we end up with a constant. It's mu naught over 8 pi. Tama ba ako? It's mu naught over 8 pi, or 0.5 times 10 to the negative 7 Henry per meter. As you can see, it's in per meter kasi nga this is derived from a meter length. So on external inductance, this is not yet inductance. This is what, flux linkage pa lang to. Okay? Okay, so this is just flux linkage divided by current, magka-cancel lang tong I. Okay? So you have a mu naught over 2 pi ln of d2 over d1. So you have 2 times 10 to the negative 7. So you can see kanina this is 8 pi, mu naught over 8 pi. So it's zero point 0.5. Now this is mu naught 2 times 10 to the negative 7 ln of d2 over d1 Henry per meter. So you have two sources of inductances actually. You have an internal inductance and external inductance. So that's the inductance total. Okay, so you just add them up and then you get the inductance. Okay, so that's the formula. Now, if you have a group of conductors, then it gets a bit complicated if you have that. Okay, where do I start? Let's say that you have this set of conductors from 1 to n. It's 1, 2, 3 to how many conductors are there, n conductors. I guess you'll see this in four wire systems. Okay, you have the neutral wire. Uh, but it's not as simple as that. Anyways, yeah, actually hindi pa pala. Hindi pa to yung sa four wire system. Uh, yeah. I guess wag muna nating isipin yung polyphase systems dito. Basta you have different sets of conductors carrying different currents. Okay? So if you're interested with the flux linkage on one, again take note flux linkage pa lang, hindi pa to yung inductance. The flux linkage on conductor 1, basically it's the flux linkage here. So the flux linkage on conductor 1 is made up of the flux linkage internal plus the flux linkage external. Okay? So the flux linkage internal, ito na 'yon. This first term here is the flux linkage internal. Okay? Now, how about the external? So, for the external, let's say that you have an arbitrary point P dito. This P will serve as your D2. It's point 2. Okay? So, well, D1 is basically your radius. D1 is just the radius. This one. This is D1. This is the radius. D2 is an arbitrary point in outside the conductor. So let's say that it is located in P. Okay, so that is D2. So you have this length 1 to P, that's D2 of conductor 1. 2 to P is D2 of conductor 2. 3 to P is D2 of conductor 3, and so on and so forth. N to P is D2 of conductor N. Okay? So for the external, take note this is just for conductor 1. For the external inductance of 1, the external flux linkage will be this one. It's D1P, that is D2 over D1, which is radius of 1. Okay. However, take note. So this the interesting part here, well, it's not really interesting because it complicates things. The the hard part here is that magnetic flux linkage 1, external, take note, external is also affected by the other conductors. So you see these terms here. 2 times 10 I2, take note, this is because take note this one is due to the current I1. This one is due to the current I1. So this is the self-inductance. Yeah. And then this one are due to the other conductors, current I2. This is due to current I2. I think this is current IN. I might have miswritten this. So that's IN. Up to the current IN. So you have one internal inductance for this flux conductor 1, but many external inductances due to the presence of other conductors. And to get that, the formula is 2p, that's D2, and for D1, it's the distance between the conductor, the subject conductor, and the neighboring conductor. 1 to 2 to 1 to n, and so on and so forth. 1 to 3, 1 to 4, and so on and so forth. Okay? So yeah, you have a very very long equation. You have this very very long equation. You can combine these two because they both have I1. they have times 10 to the negative 7. Yeah, they have the same times 10 to the negative 7. These two, this can be represented as 4 over 2. Yeah. So essentially what will happen here is you can take out this 2 times 10 to the negative 7. So that's what will happen here. You can represent this as 2 times 10 to the negative 7. This 2 as 2 times 10 to the negative 7 divided by 4. Yeah, this is 2 over 4. Okay. So this point 5, this can be 2 over 4. Okay, so now you have a 2i1 times 10 to the negative 7 divided by 4. That is this one. So now you have 2 times 10 to the negative 7 as a constant for these two terms. So you can take that out and then that will be i1 over 4. Okay? And yeah, you have this over 4. Uh, as you can see, we don't have an over 4 here, but what happens is you have an R1 prime here versus an R1 here. So what happened there, excuse me, your over 4 here is integrated within your ln. So pumasok siya sa ln. So this R1 prime is actually R1 raised to negative 1/4. Okay? So I guess I leave that to you kung paano na ipasok yung 4 sa loob ng ln. I leave that to you. Yeah. And then for the other terms, so yun pa rin siya. And then I guess the beauty of this equation is that itong 2 times 10 to the negative 7, pwede na natin siyang ilabas. And then you have I1, I2, and so on and so forth. In. Okay? So that's the beauty of that equation. Excuse me. Now, uh, you cannot divide this by I1 specifically kasi I1, I2, and IN is not necessarily equal. So, ganun lang siya. Okay, hindi kasi siya equal eh. Okay. However, yeah, in a three-phase system, these currents will equate to 0. So you can represent IN as this equation, negative of all of the currents going in to the neutral point. Okay? So you have an I1, I2, and this is IN. So and so forth up to IN. Okay? Take notes in Weber per meter, Weber per meter. Okay? Yeah. Okay, there is a very, very long derivation here. I guess I'll just skip that. Okay. I will go to this one. If P is very, very far, so the thing about P is that if it's very, very far, such that your arbitrary point considered is, let's say, it goes a very, very far distance, that your 1P divided by NP, the ratio of 1P and NP, basically this ratio is approximately equal to 1. So they are almost similar in with respect to the distance of P. With respect to their distance with P, they are almost similar. So you get them you get this as approximately equal to 1. So what happens here is that this 1P over NP and all of these 2P NP will just cancel out. It's an approximation that is done using the assumption that P is very, very far. Okay, so how did we end up here? So I guess again yung derivation nasa slides before. Okay, so well, yeah, the idea is you now have this equation. Yan, mas it's wala pa siya masyadong pinagbago dun sa nauna. Wala pa siya masyadong pinagbago, but now instead of d2p over d12, it's now d1n over d12. Okay. Yeah, and all of them are in terms of D1N. Okay, so pare-parehas na silang naka D1N, D1N, D1N. Okay? So yeah, you can separate these two. I guess, ang daming derivation nito. Anyways, you can separate the numerator and the denominator from the LNs, on the LNs. So you now have two sets of LNs, one for the denominators, one for the uh, numerators. But, well, it will simplify things later on kasi you will have this and then, where is that? Haba naman. Yeah, I guess dito tayo. Punta tayo rito. This one, pwede nyong ilabas yung LND1N. Ay, yung mga LND1N. Okay. So that is LND1N. Now, negative LND1N is equal to negative of LN, 1 over D1N. So ito yon. Okay? Kapag nilabas mo siya, you have an I1 plus I2 and so on and so forth plus IN minus 1. So yung negative ng LN kanina, you can associate that with this sum. Then this is now equal to IN. So bumalik lang tayo sa IN. Okay? Yeah. So yun. Bumalik lang tayo sa IN. And then you have this I1 ln plus I2 ln plus and so on and so forth. In minus 1 ln up to in ln. But the good thing here is, kung mapapansin nyo, all of the numerators are now 1. All of the denominators are just distances. R1 prime, it's basically R1 e raised to negative 1/4. D12, it's the distance between 1, 2. D1 to n minus 1, it's D1 to 3, D1 to 4, D1 to 5, and so on and so forth hanggang D1 to n. So it's basically the distances nitong mga mutual conductors na ito, nitong mga neighboring conductors. So you eliminate the distance from 1 to p, from 2 to p, 3 to p, and so on and so forth. Nawala na siya. Okay? So your inductance now is just a function of these distances from 1 to 2, 1 to 3, and 1 to n. Okay? So, yeah, that's why it's simpler. So, yun yung pinuntahan ng mahabang derivation na yun. Okay? So, the simplest form is I1 ln 1 over R1. R1 prime, sorry, R1 prime. Yan yung dito sa conductor na to. I2, para dito sa conductor na to, ln ng 1 over D12, the distance between 1 and 2. I3, sige, let's make this I3, ln of 1 over D13. So, yung current dito times ln of the distance, 1 over the distance between 1 and 3, and so on and so forth hanggang sa kung ilan mang conductor. So that's for the mutual flux linkage between, on conductor 1. So, on conductor 2, we'll just use the same formula, but instead of I1 here, this is I2, ln ng 1 over R2 prime. Then this is I1, ln ng 1 over D21 from 2 to 1. Of course, you don't have a D22. I guess yun na yung point ng R1 prime. Then you have, you have an I3, ln ng 1 over D23. And so on and so forth hanggang n conductors. Okay? So that's how you get the flux linkage between on a conductor. Okay? As you can see, hindi pa tayo maka-proceed sa flux kasi sa inductance kasi hindi pa natin siya kayang i-divide into current. Hindi pa natin kayang i-divide yung current. Yeah, hindi pa natin kayang i-divide yung current. So hindi pa tayo maka-proceed sa flux. Okay? Kaya ba nito? Weber per meter. Yeah, para parehas lang siya. Okay. Yeah, okay. So, if you have a single phase line, you have this. Meron din tayong three-phase line dito. And composite, no, it's composite conductors. Yeah, composite conductors. Yeah. And then, three-phase lines, meron din later on. But I guess yun lang muna. So at least may idea na tayo on the difference between internal and external inductance and how does your neighboring conductors affect the external inductance of one conductor, and how do they affect each other. So yeah, that's it. Yun lang muna. Okay, I'll see you soon.